maybe. I guess I'll just stand still. Thank you for the invitation to talk. I'm going to be discussing today the numerical integration of the Lorenz-96 system with scalar additive noise. This is in the same flavor, say, of earlier talks today in terms of, well, stochastic model reduction and these themes, but we're taking a little bit more of a reductive approach, and in part because we want to, well, provide some rigorous analysis in terms of how to produce mathematically consistent results in what is, I mean, the most common benchmark system for DA, and as well, I mean, to explore some higher order themes in terms of ensemble forecasting through this discussion. So in particular, let's see, as an outline, we'll just discuss briefly, I mean, twin experiments and toy models, then discuss, say, its relationship to multi-scale model reduction and say, well, error in random dynamical systems, as well, then look at, say, several stochastic integration schemes and say their effects in terms of model bias on the model statistics. And we'll look at, say, several numerical benchmarks, including so strong and weak convergence, ensemble forecasting statistics, and filtering statistics, which will lead us to our conclusions and our future work. So let's say everyone here is aware that ensemble forecasting and data assimilation have become the prevailing modes of prediction and uncertainty quantification within geophysical modeling, where DA combines so physics-based numerical models with real-world observations of a physical process. Wherein a Bayesian framework, we can see, say, the ensemble-based forecast basically as a sampling procedure for what we can call a forecast prior probability density. That with respect to which our physics-based numerical model and say, well, our previous estimates of the state basically encapsulate our Bayesian prior knowledge. Now, the output of DA in this Bayesian framework is, say, a posterior probability density for the numerically simulated state, or just at least producing some statistic of that. The interest then is, say, well, bias in the forecast prior will introduce bias into the posterior probability density. And therefore, say, understanding and quantifying model bias has become a rather central discussion in terms of ensemble forecasting and DA. So there's, a wide discussion currently in terms of, well, numerical precision and, say, well, bias in, say, the output statistics of models. And, say, two, well, elements of this, and from a little bit different standpoints we've seen, it's been noted, say, quite recently, that the numerical precision of, say, the ensemble forecast can be substantially reduced without a major deterioration of the DA cycle relative predictive performance when we have a deterministic but biased model. And this is intuitive in the sense that, well, the model error basically overwhelms all the errors that are introduced to, say, the discretization. The precision of the numerical forecast. And that's it. The forecast deteriorates. Well, let's say not that the forecast deteriorates, but say it's overwhelmed with respect to, this was, I think, in the speedy model, and say they reduced, let's say, the numerical discretization precision, and say they found that, especially in this case, they could, well, achieve comparable results with a low precision model, and say, quite possibly, say, remediate these effects by, say, running more samples in the forecast. And this would actually be, say, no worries. This would actually be, say, a preferable alternative. But on the other hand, we've also seen, say, for, well, random unbiased models, that there's often, say, differences in the statistics of the model forecasts of stochastic dynamical systems due to discretization errors of low-order solvers, where one particular example, Frank and Gottwald have shown that, say, well, they had to actually introduce an order 2.0 Taylor scheme to correct the bias in the drift term that was introduced with respect to basically an Euler-Maruyama discretization. What we want to add to this discussion now is particularly, well, answer some questions in terms of how and to what extent, say, bias in numerical schemes of random dynamical systems will also bias twin experiment and DA statistics. And, say, in this discussion of sort of low precision numerics and how we can best target, I mean, the effort and the computation, well, how can numerical precision be targeted for unbiased prior estimates in these ensemble forecasts? So our test case is basically motivated by the two-layer Lorenz system, in which, say, this simulates coupled ocean-atmosphere dynamics. And it's a quite common system for studying stochastic model reduction. In particular, so the effects of, say, the fast variable dynamics on the slow variables can often be parameterized with a stochastic process. And it's justified mathematically with respect to, well, the central limit theorem, in which, when we have, say, the separation of the timescales between the fast and the slow variables taken to the asymptotic limit, the effect of the fast variables can be reduced to additive Gaussian noise. But say, as a note, in the finite separation of scales, this sort of whitened time model error assumption is no longer valid. And in general, we need to include non-Markovian memory effects in the process. The test system that we study in this case, we denote the L96S model, in which we define it here with F being, say, the standard single-layer Lorenz deterministic component. We have this just being the identity matrix. W will be, say, a n-dimensional Wiener process, and S will be an R to R measurable function of possibly time-varying diffusion coefficients. In this case, say, both the model and the truth twin will be simulated with respect to this model, where the numerical model, therefore, is unbiased in representing the true physics, but we assume that the true physics are going to be intrinsically random. This, say, corresponding to the last slide, is basically an idealized version of the two-layer Lorenz-96 model in which the separation of the timescales has been taken to infinity. And say, we can denote in, say, filtering nomenclature, this corresponds to a perfect random model. This we use in particular to distinguish the effects, well, of numerical bias from bias in, say, the physical process model. Now, we need to make a distinction in terms of mode of convergence with respect to, well, the numerical schemes in which we study. Say, particularly, we're going to look at schemes which converge in the strong sense, whereby, say, strong convergence measures the expected path discretization errors over all possible realizations of the Wiener process, starting at some initial condition. And it's the analog, let's say, of the standard path discretization error in a deterministic system. We can define this a little bit more rigorously by saying if we have, say, XSP will be just an exact sample path with respect to some realization, and X will be an approximation of this path, discretized at a maximum time step of delta. Loosely, well, we'll say the approximate X converges to the sample path strongly at an order gamma if there exists, say, some delta sufficiently small, some constant which is fixed, such that for every delta taking lower than this threshold, then the expected path discretization error is bounded, say, as the expectation of the absolute difference of the two paths with respect to this constant and delta taken to the gamma, where these are evolved, say, to this forward time t. Now we distinguish this from, say, weak convergence, which essentially measures, say, the error in representing some statistic of the forward distribution, where if we have an initial point Dirac delta and we want to study, say, this distribution and its evolution with respect to all possible realizations of the Wiener process. If G is, say, some statistic that's 2 times gamma plus 1, continuously differentiable, and of at most polynomial growth, then we say this approximate X converges weakly to, say, the true path at order gamma if, say, for all delta sufficiently small, we now include, say, the expectation within, say, the norm of the difference. So we're looking at, say, well, the difference of the expected value of these two, of the statistic with respect to these two initial conditions of all forward in time. Loosely, I mean, this can be understood sort of intuitively as strong convergence measures the path, the mean of the path discretization errors, whereas weak convergence can, for instance, represent, say, the error in representing the mean over all, say, possible realizations of this Wiener process. So one thing that we'll note about this, then, is that strong integration schemes do converge in the weak sense. But however, weak schemes in general aren't guaranteed to converge in the strong sense. And say for twin experiments, this distinction is actually important, whereby, say, the truth twin, well, should be generated by, say, some scheme that's, say, precise in the strong sense. Because here we assume that we have observations of the path that are consistent with the governing dynamics. But whereas, say, the ensemble forecast need only actually be, say, precise in the weak sense, because we only need to, say, get a representation of the prior. That is, say, well, if we're trying to represent this forward sampling density, we don't need to ensure the precision of each path as long as the density itself is accurate. Therefore, the model twin should be evaluated in the weak sense. Now, we'll study, say, 3 commonly used integration schemes in this system. Or say particularly Euler-Maruyama, which with respect to this system has order 1.0 convergence. The 4-stage Runge-Kutta going to Rummelin, which in this system has order 1.0 strong convergence. And say the second order Taylor scheme, which is based on, say, a second order Taylor-Stratonovich expansion of the equations. Now, just as a note, it's not the focus of this talk, but say the derivation of this is non-trivial, and to our knowledge, it hasn't earlier appeared in the literature. And say particularly because, say, I mean, this reductive form of the system, because it has, say, constant or vanishing second derivatives in the deterministic component, it has periodic boundary conditions, and because of the additive scalar noise assumption, this can actually be computed efficiently with complexity that only grows linearly in the system dimension n. So let's start getting into some benchmarks. We'll estimate, say, the strong convergence discretization error in the vertical axis with respect to, say, the integration step size in the horizontal axis, where this is all in log base 10 scale. And say our point estimates, say for the strong discretization error, are generated by the average estimated discretization error over 500 independent batches of simulations, in which each batch evolves one initial condition with respect to 100 independent realizations of the Wiener process, where we simulate now, say, our sort of benchmark sample path. It's a finely discretized solution with error on the order of 10 to the minus 7. And say each one of these, Euler-Maruyama, Runge-Kutta, and Taylor, will be simulated, well, with a coarser approximation with respect to which we now consider the difference with the finely discretized solution. Let's see. So our strong convergence, this, well, say, expected path discretization error is estimated now as the mean difference of the finely discretized solution versus the coarse discretization over all Wiener processes in the batch. And say, it's known that, say, well, for batch sizes sufficiently large, the batch estimates themselves are Gaussian random variables distributed around the true expectation. And therefore, say, the slope, or say, the order of convergence, can be estimated with weighted least squares, where in this case we take weights proportional to the inverse standard deviation of the batch realizations. Now, so the diffusion level is fixed in each panel, where we range basically from a low diffusion to a high diffusion regime. And we note, say, well, the orders of convergence are all empirically verified within this graph. But the constant C actually has a large impact on the strong discretization error. Or say in particular, if you look at the low diffusion regime, we note that, say, our order 1.0 Runge-Kutta scheme actually has discretization error that's comparable to the order 2.0 Taylor scheme. The performance of the Runge-Kutta scheme as well actually varies strongly with respect to low and high diffusion levels. But say, while the order of convergence is the same with respect to all regimes, the difference of the performance, again, is reflected with respect to this constant C. Now, this is the same plot, but say with respect to weak convergence. Here, again, now we just have, say, the absolute difference on the outside of the expectation, where this is estimated as the difference of the means of the finely discretized solution and the mean of the coarse discretization with respect to all, say, realizations of the Wiener process in the batch. And the effect, actually, is even more pronounced in the weak regime, in the sense that, say, in low diffusion, we see that actually the 1.0 method is actually outcompeting, say, the order 2.0 method. Here, say, again, the weak discretization error for Runge-Kutta is varying on an order of magnitude between low and high diffusion levels. And say, this suggests, say, for twin experiments, that say, well, the high precision across all diffusion regimes makes Taylor a reasonable choice for generating the truth twin. But whereas the Runge-Kutta can perhaps generate ensemble forecasts for the model twin for its high weak accuracy. Now, so in the following, so we want to extend these just simple numerical benchmarks to actually study, say, the ensemble forecast statistics and the DA statistics. And say, in this case, we'll use Taylor as basically a standard benchmark in all of these experiments because Taylor, well, I mean, is consistent across all diffusion levels. And so it leads to just a standard benchmark for these other methods. We study in particular how the ensemble statistics of Euler-Maruyama and the Runge-Kutta scheme differ from Taylor over, say, well, several different benchmarks. So in this plot, we have generated 500 initial conditions of this model, and say each initial condition is then forecasted with respect to 100 independent realizations of the Wiener process. We compute then the empirical ensemble estimated mean and ensemble estimated spread of the forward density with respect to this initial condition evolved forward in time. And then this is performed over each of the schemes as follows. We use Taylor with a step size of 10 to the minus 3. We use Euler-Maruyama with step size 10 to the minus 3. And we use Runge-Kutta with a step size of 10 to the minus 3. So this is our fine discretization benchmark for the ensemble forecast statistics. In the top panel, we have the root mean square deviation of the ensemble means for Euler-Maruyama plotted in this cyan and Runge-Kutta plotted in this orange versus, say, again, the difference of the ensemble mean versus that of Taylor. In the bottom panels, then, we have the ratio of the ensemble spreads, again, for Euler-Maruyama and for Runge-Kutta versus Taylor. Now, what we plot here are the summary statistics of the, say, forward density over these realizations versus time over these initial conditions, where the median is plotted as the solid line, the 80 percentile is plotted and shaded, and the minimum and maximum values are plotted and dashed. What we note then is that, well, the Runge-Kutta actually has almost no difference, say, between the Taylor scheme for forecast time up to t equals 3. Please.
Apologies, but could you just say again how you're measuring the error or the goodness or the...
We're taking, say, compute the mean over, say, the 100 independent realizations, the Wiener process. With
ensemble mean.
Exactly.
And measuring...
The root mean square deviation. Exactly.
Thank you.
Yeah, no worries. And let's say this is also, just as a note, this is reflected again in the spread, where the spread is about 1 up to forecast times about t equal to 3. But whereas the Euler-Maruyama scheme actually experiences rapid divergence in the means and say, well, divergence and presence of bias in the spread, particularly, it's hard to see here, but it is, say, the median spread ratio is actually above 1.0 asymptotically. Now, we take a coarser discretization in this plot, same plot as the last, but in this case, we now have, again, Taylor simulated with the same fine discretization, but we simulate Euler-Maruyama and Runge-Kutta with step sizes of 10 to the minus 2. In this case, so Runge-Kutta, well, the ensemble mean basically has a faster onset of divergence, and the ensemble spread has some increased variance in, say, the ratio of the spreads. But this is contrasted, say, with Euler-Maruyama, which has an extreme divergence, and say, especially in low diffusion. And say, the ensemble spread, which again has divergence and the presence of bias, where here, actually, the minimum spread is indeed above 1.0 asymptotically. So what we note here is that Runge-Kutta does not have, say, this sort of extreme divergence of trajectories, and the spread remains unbiased asymptotically in contrast to Euler-Maruyama. Now, as a quick summary of what we saw, so Runge-Kutta we found so far is robust in generating ensemble forecast statistics, where it's actually quite precise in the weak sense. And say even for a coarse discretization in the time step, it's unbiased in the spread as compared with the Taylor using a much finer discretization. And the divergence of ensemble means matches the asymptotic divergence, say even when we're using a finer time step in the Runge-Kutta. The low precision numerics, effectively, it increases the variance of the sample forecast statistics, but they remain unbiased in sort of the asymptotic outputs. Whereas for Euler-Maruyama, we have systematic biases in the ensemble forecast statistics, and in terms of the asymptotic ensemble spread, it's systematically and artificially inflated due to the low order of, say, this discretization. As well, as noted, it has extreme divergence of trajectories, where the divergence is over an order of magnitude difference compared with the Runge-Kutta scheme. Now, this indicates that Euler-Maruyama biases the ensemble forecast statistics, but this hasn't yet demonstrated that it actually has bias on the DA statistics, which we demonstrate now in the following. So here is our sort of benchmark Taylor system, in which in our benchmark configuration, the truth twin is generated with Taylor with this fine time step, 10 to the minus 3, and the model twin will be as well with the same time step. What we plot are, say, the ENKF, RMSE, and spread, where in the vertical axis we have the diffusion level S, and say in the horizontal axis we have the variance of the error in the observations given to the ENKF. Now, we use 10 to the 2 samples with the state dimension of 10, and it's fully observed, such that the convergence of the filtering statistics can occur without, say, any sort of a tuning with respect to inflation or localization. The RMSE and spread are then computed as the asymptotic average over 2.5 times 10 to the 4 analysis cycles. And we see that the analysis RMSE is comparable to the analysis spread in all these regimes, and is lower than the standard deviation in the error of the observations, indicating that we have indeed stable filter statistics. Now, as comparison, we want to look at if we vary the ensemble integration between Runge-Kutta and Euler-Maruyama with the step size between this fine discretization and this coarse discretization. Now, what we see here, we're going to look at, say, the ensemble forecast being generated by Runge-Kutta, and again, the truth twin will be generated by the Taylor scheme, where, so again, we generate this with Runge-Kutta and compare, say, the difference in the RMSE with the benchmark in all these regimes for the ENKF, and the ratio of the spread for the ENKF with the benchmark system. What we note, actually not pictured here, is that in the fine time step of 10 to the minus 3, the filtering statistics for the Runge-Kutta generated ensemble actually differ basically on the order of 10 to the minus 6. There's effectively no difference between this and the Taylor scheme. Not pictured here because it's trivial. But say when we have this coarser time step, 10 to the minus 2, this introduces basically small errors, as you can see in these differences in sort of the RMSE and the ratio of spreads. But the residuals themselves are actually unstructured in sign or magnitude. This indicates that this is effectively just random, unbiased numerical noise. This is contrasted now with Euler-Maruyama, where, say, we generate now the ensemble with Euler-Maruyama with a step size of 10 to the minus 3, the fine discretization, and we see actually quite clear structure in the residuals. There's artificial inflation, once again, in the forecast, and say, in high diffusion, we note, say, there's almost no difference between this, well, finely discretized Euler scheme and the higher order Taylor scheme. But say, the bias, therefore, depends strongly on the level of the model uncertainty in the system, basically as, say, the level of diffusion goes up or down. This is now contrasted, again, where now we generate the ensemble with Euler-Maruyama and take the coarse time step. And while we note, say, the structure in the residuals persists and the artificial inflation of the forecast persists as well, but say particularly in low diffusion, say the error in the discretization actually forces filter divergence, where the RMSE is actually on order 1, say, in these low regimes. In high diffusion, this difference is, again, it's a bit relaxed due to the model uncertainty. Now, say as a final benchmark, we want to see if we, well, relax, say, the discretization of the Taylor scheme generating the truth twin. And say, in particular, this is for the model twin being generated by Runge-Kutta with step size 10 to the minus 2. And the truth twin, Taylor will have step size 5 times 10 to the minus 3. In this case, so the expected discretization error due to, say, our construction and, say, our benchmarks for both the Taylor scheme and for, say, the Runge-Kutta scheme, this enforces discretization error in both the truth twin and the ensemble forecast less than 10 to minus 3 over all regimes. And what we note, well, say the inaccuracy in the truth twin, actually now it appears that there's some structure in the residuals with respect to this, but the results are largely as the same as with the more accurate truth twin. Compared with, say, the model twin with Euler-Maruyama and the truth twin being generated by this less accurate Taylor, it relaxes, say, some of the issues in Euler-Maruyama when the model twin uses this fine discretization. But yet, the filter divergence still occurs when we have, say, the model twin using this sort of coarse discretization. So, as just conclusions on this, we distinguish, well, between strong and weak convergence and, say, the, well, impact and importance for the truth twin and the model twin, respectively. For Euler-Maruyama, we see that it introduces strong systematic bias in twin experiments when the step size is greater than or equal to 10 to the minus 2, which is about what, we typically afford in a twin experiment. The effect, though, strongly depends on the model uncertainty in the twin experiment, corroborating some of the earlier results in the 2 articles that we saw at the beginning of this. The bias, however, in particular, is sufficient to cause, say, filter divergence in weak diffusion. Whereas for the Runge-Kutta, it's a statistically robust solver. And say, when the discretization is on the order of 10 to the minus 3, there's virtually no difference from the higher order method. When we have, say, this coarser discretization, it introduces additional error, but the error doesn't strongly influence, say, the RMSE or the spread of, say, the ensemble or the DA statistics. So we demonstrate, say, by using our numerical benchmarks, that by using the configuration that we propose with a slightly coarser Taylor scheme and, say, well, the coarse Runge-Kutta, that we can bound the overall discretization error. Again, so using Runge-Kutta with 10 to the minus 2, and Taylor with 5 times 10 to the minus 3, where this forms now a practical compromise based on our diagnostics that doesn't, say, influence or bias the outcome of filtering statistics for twin experiments. Moreover, so this gives us now a, well, mathematically robust configuration for DA twin experiments to have mathematically consistent, well, twin experiments for benchmarking filters, for instance. We also, in our work, again, not the focus of this, but we've provided a novel derivation of the order 2.0 Taylor scheme in the system. And yeah, as far as we know, this, say, actual derivation hasn't been derived previously. And we provide basically benchmarks, say, for all of these schemes in this work. What this leads us to, though, and say this higher order question about, well, filtering in DA is, well, particularly, can weak schemes, which may not converge to any sample path in particular, reduce the computational burden of ensemble forecasts in geophysical models? If the goal, in particular, is to converge in distribution alone, this actually may be a viable alternative, say, to traditional geophysical modeling paradigms, with the potential advantage that numerical precision can be targeted in the weak sense alone. And that's it.
Questions?
Thank you very much, Colin. What about the Milstein scheme compared with...
The Milstein scheme is actually identical in this case because of the scalar additive noise condition. There's no, say, correction that's needed to, well, fix, say, the Ito-Taylor expansion.
Thank you for your talk. It was great. I really like the giant ensembles, your 500-member ensembles. It seems a bit of a shame to me to invest that much on the ensembles and then throw all that information away by taking the mean. So my question really is, how Gaussian are those distributions, in which case you really don't need 500 members? And if they're not Gaussian, then you really don't want to use RMS error. So you can choose which. I mean, makes sense?
Yeah. No, I think that's a quite valid point. We haven't actually studied, I guess, how non-Gaussian they are. I mean, only, say, for a few weak benchmarks, I mean, skewedness, kurtosis are present, say, within, say, these forecast ensembles. And so perhaps, exactly, I mean, the mean may not be the best possible benchmark. I guess we've chosen it mainly because these are the most common benchmarks for these types of experiments. But I think it's a quite valid question.
Okay. Any other question? No? Okay, thank you very much, Colin.
Thank you.